Hey guys, welcome back. This is going to be ICND 2, Session 3, Part 1. So we're a little bit thrown off this week because it's Thursday. Normally that would be the last class of the week. However, today, this was Labor Day week, so we began on a Monday, so we're a little bit behind. Thank you guys once again for joining me. We're moving forwards, upwards, and onwards through the OSI model and into our courseware this afternoon, this evening, depending on your time zone. And what we're going to start off with today is going to be Layer 3 redundancy. So the way that you think about this is, Layer 3, that's obviously routing. We're going to move into a classification or category of protocols called first hop redundancy protocols. First hop redundancy protocol. It gives away what we're about to cover, right? If you look at your computer or tablet or smartphone or printer, they all have a default gateway, right? What happens if that default gateway, which is in fact your first hop, were to go down? Well, you're not going to get anywhere. The whole rest of the world is out there waiting, but if your first hop is down, you're dead in the water. So first hop redundancy protocols, as the name suggests, it gives us the ability to have multiple layer 3 capable devices. And should one go down, the other one can detect that. He's basically listening for a heartbeat or hello information. And when the first device goes down, the second one can take over using that same IP address and the same MAC address. This ensures that the routing information and the ARP cache that each client will already have stored is going to be accurate. So quick overview of what we're about to cover. You've got two routers or layer 3 devices. It could be switches as well, using your switch virtual interfaces, right? Looking at our pair of routers or pair of switches that are serving as the gateway as the client, we say this is the primary, and he's going to always route traffic. But should the primary fail, the IP address of the primary is going to move over here to the secondary. And when it does, so does the MAC address. And then what happens is that all the users are going to send their traffic to the second router, and they're not going to realize that there was a failure. So that's the first topic. The second topic for today is going to be troubleshooting. So I don't know, I think it's going to be a pretty good time. This whole class is a good time. Every day there's new good things to talk about. But this is a pretty good one as well. I think even it stands out on its own. So let's jump over here and let's see, right there and then right here. All right, good. So these are back to our slides. Understanding layer 3 redundancy, which is also known as first hop redundancy protocols, or FHRP. This would be the category of Cisco configuration if you're looking through documentation trying to figure out how you would set this up. So here's what's going on in our scenario. We've got a need for gateway redundancy. We've got router 1, we've got router 2. This isn't the best diagram, so let's imagine that it's not about reaching that server. Let's imagine that each of these routers is going to get you access to the internet. And if one of these devices goes down, the other one has access, but you don't know to use it. So what you'd normally do is you'd have an IP address on router A, a IP address on router B, and if router A fails for some reason, I've got to go into this client and manually change his gateway to point to .3. Is anybody looking forward to doing that? Going into all of your devices and reconfiguring what they use as a default gateway. Probably no one. Okay, at least Reggie says definitely not. That's going to take way too long. So here's some other things. If we wanted to, what we could do is create what we call a virtual IP address. And we're going to have it be as .1. Each of our users will set their gateway to .1, and .1 being a virtual IP that corresponds to a virtual MAC address, this will be portable. So router A can hang on to .1 so long as he's up. Should he fail for some reason, this guy will become .1, and he'll maintain that same MAC address. Why is it important that the IP moves as well as the MAC address? That's an important concept to understand. Why is it important that the MAC address moves as well? So the switch can still get you to the router, Well, it's not so much about the switch. Mark, you're on the right path. It's about the ARP, right? These guys did ARPs previously, and they have existing ARP cache. So their ARP cache thinks that .1 equals some MAC address. If I just move the IP address over and not the MAC address, everybody would be sending their traffic to the old MAC address until their ARP cache ran out. Does that make sense? Awesome. Okay, cool. So there's actually a process here where router B, when he becomes active, he sends out a broadcast frame. And this is called a gratuitous ARP. He says, I know that nobody just sent me an ARP request, but I'm going to say from my source MAC address, and this is really going to be the virtual MAC that he just obtained, he sends a message to the broadcast saying, hey, just so you know, .1 equals this virtual MAC. The reason that we do this is so that intermediate switches can go, oh, I thought the virtual MAC address was located over there, but it's not, it's located over here. So when he sends out that broadcast frame, it goes through the entire VLAN. And all of the switches now learn that they can use this path to get to that virtual MAC address. Does that make sense? There will be a broadcast that's sent after the failover. So there's two major components. There's a failover that's going to occur, and when it occurs, the two big components are the IP address and the MAC. We could just move the IP address over, but you'd have some users that could get out immediately, and you'd have others that would take up to 5 minutes before their ARP cache expires and they send out a new ARP request to learn the new MAC address. So what we do with our first hop redundancy protocols is we have a virtual IP and a virtual MAC, and it's portable from one router to the other. And whoever the active router is, when they go from the state of standby to active, they make sure that they send out a broadcast frame. So it gets flooded everywhere within that broadcast domain that says, I have that source MAC address. So if you're trying to get there, send your traffic over here. That gets all the switches to update their MAC address tables, so they now know to forward their frames to the new router out different ports. So hopefully that all makes sense. If you got it, great, because we're just on the first slide talking about why people need default gateway redundancy. We still have a ways to go. Did we show how to configure this? Absolutely not. We're just saying, for some of you guys that might be feeling a little bit lost or felt like we got started too fast, look at this. We got two routers. If one router fails, we're in trouble because everybody's gateway is pointed to .2. We would have to change it to say .3. Well, that would be miserable. So we set up a virtual IP address using a protocol like HSRP, VRRP, or GLBP. There's 3 protocols that you have to choose from. HSRP is the one that Cisco invented. You know how this works. Years later, there was finally a standard. It's called VRRP, and Cisco supports that too. Cisco then took this and took it one step further and made it better with something called GLBP, Gateway Load Balancing Protocol. We talked about the term load balancing yesterday, and this does real load balancing. It looks at the utilization of the two routers, and it will steer the user to the router with the lightest load. So these are listed in the chronological order that they came out in. First there was HSRP, then VRRP, then GLBP. So far, so good? We haven't looked at the configuration or at these protocols yet. We're introducing high-level concepts. Our high-level concept for this slide is the virtual router. So we've got this IP address .2 and IP address .3, and I know there's 2 physical routers here, but what we want to think is that there's a virtual router. In other words, there's a virtual IP and virtual MAC address that you could move between the active router and the standby router. That's what I was describing in the last story, probably 2 times in a row. Yeah, no problem, Gavin. So over here, what we see happening is the standby router goes down, the other router takes control of the virtual router, which sounds funny. I think it makes more sense to say this backup router saw that the primary went down. He hasn't received a hello message in a very long time. A very long time for him is going to be about 3 seconds. When that 3-second window expires where we haven't heard hellos, we go, up, my neighbor must be missing. Let's go ahead and take that over. So he takes over the virtual IP address, he associates it with his interface, and also the virtual MAC. Those now go active on this device. When they go active, we send out a broadcast frame so that this switch knows the virtual MAC is over here on port 2, and it's no longer on port 1. We send out a broadcast frame so that he updates his MAC address table. Does that make sense? So there's a little bit that's complicated with this redundant gateway. If our gateway dies for some reason, we need a stable way of updating it, and we've got to think about the ARP cache of the user. That's one of our concerns, and we've got to think about the MAC address table on the switch. The way that we handle these two is we move the IP address and MAC together from one router to the other. ARP cache is solved. The second piece, we send a broadcast packet from the virtual MAC. The reason for this is so all our switches can update our MAC address table, and immediately all traffic will now come to the forwarding router. So HSRP is Hot Standby Router Protocol. It defines a group of routers, more than one. One will be active, one will be standby. There will be a virtual IP address and virtual MAC. That's what defines this virtual router. So there's an IP address and a MAC, and they're basically shared, or you could say supported by, your two physical routers. Everything that we do to build HSRP is with the standby command. So one of the cool things that you'll learn when you configure things in Cisco, it's true most of the time anyhow, is when you configure something, you can, if I configure it with standby, I can obviously remove it with no standby, but that I can also see a lot of the attributes regarding that protocol or service with the show standby command. So everything we're going to configure will be standby, and we'll validate it all with show standby. Looks like I got a question already. It says, how do you make sure the virtual MAC is not a duplicate since it is not hard-coded? So it's little times like this that you and I get to spend together where we get to learn how networks really work. And don't feel bad. I'm learning every day. I've been doing this. I moved over to education just because I liked learning so much. I get to learn the most as a trainer. And I've been doing this forever. I say forever, about 12, 13 years. I've read a lot of books, a lot of certs, and I'm still learning brand new stuff every day. So, for example, you say, how do we make sure that that virtual MAC isn't duplicate? It needs to be unique, doesn't it? Or does it? See, duplicate MAC addresses, believe it or not, aren't really a problem. Neither are duplicate IPs. You think they are, but they're not. It's only a problem when they are within the same broadcast domain. There will be times where you have the same IP address in different locations around the globe. People will do this as a means of load balancing, and it's referred to as anycast. You can read about it on Wikipedia. Can't really go into it now, but trust me, it's out there. The other thing that we're going to learn is that MAC addresses can be duplicate. That's totally fine. The MAC address is only important within your broadcast domain. Most of the time, our broadcast domains only have room if it's a /24. We've only got room for up to 254 devices. So the chance of a MAC address conflict is pretty slim, but the chance of using the same MAC address in many places is actually really high. Let's step away from the courseware for a second, and I'll show you exactly how this works. You know what? Let's just pop over here. Instead of whiteboarding it, I'll take you to Wikipedia. Let's just say HSRP virtual MAC. So what's going to happen with your HSRP, when you create that virtual IP address, it's part of a standby group. A standby group is what they call a virtual router. So if you look at what's going on behind the scenes, I wish we could have a white paper instead of a forum. I want to find something definitive not something that's a question. So here's HSRP, here's an RFC on it back from 1998, and what I'm just looking for is a virtual MAC. I think it's 0100 is what it's going to start off with, 0100. And I think they're going to show it to me, and they're going to show it to me in a really cryptic format. I don't want to read it like this. I want to show you something better. Let's see if this tells us. Configuring the virtual MAC address. So HSRP will use a virtual MAC address. They're not going to show us what it is. There's a prefix to it. Rabble. So when you set up HSRP, it uses this virtual MAC. But part of the virtual MAC, in these last two digits here, see, like HSRP version 1 uses the MAC address range of all zeros, 0C, and then 07AC00. Now the significance here, when you look at these MAC addresses, is the last byte. The last byte is right here. This is hexadecimal. A byte is 8 bits, but 8 bits in hex can be covered with only 2 spaces because the maximum character is F, and FF equals 255. So what you would write out with 8 lines of binary, we can do basically 2 characters of hex. Everybody with me? Just nod if you can understand hex. Everyone's smiling and nodding. All right. I see some thumbs up. So this is kind of cool. When you create a virtual router, it goes into something called a standby group. The last 2 characters of your MAC address are based on your standby group. So if my standby group is 1, my MAC address would be all these characters with 01 at the end. Does that make sense? And if it was standby group 10, it would be all those characters with an A at the end, because A is 10 in hex. So addressing Fenton, it wasn't Fenton's question, it was Mark's question. How do we deal with duplicate MACs? You're going to have duplicate MACs. Everybody who creates standby group 1, which is, I say this in satire, but kind of, everybody who sets up HSRP, it's like pick a group number between 1 and 255. What would you pick? This is my first HSRP group. I just sat down on my layer 3 switch. It says pick a number from 1 to 255. The number that you would pick right now, put it in room chat. Everybody's got to play or it doesn't work. Come on. All you're doing is picking a number from 1 to 255. So Mark picked number 17, but I've got a bunch of other people that go, I would pick number 1. Well, guess what? I picked number 1 too. So what happens is that every one of us that chose the number 1, and most of my customers just happened to use 1 because that was the first number, they're all going to have the exact same MAC address. But the MAC address is only important within their broadcast domain. Make sense? So you will have duplicate MAC addresses. You're supposed to. It's not a big deal. Good stuff to think about, though. A lot of times that's something that's true, but you don't really think about it, and no one ever points it out. So looking at HSRP, this was the first stab at a first hop redundancy protocol. I keep saying this because, when I learned this, no one ever told me FHRP. So I would dig through documentation guides to try to find out how to configure this stuff and what options were available and if we could tweak it or tune it to make it work faster. And it's all categorized in Cisco documentation under the category of first hop redundancy protocol. That's where they'll actually list HSRP, VRRP, and GLBP. So HSRP was the first at Cisco proprietary. Then a standard came along called VRRP. This is what we could run. Maybe one router is Cisco, and my other router is Juniper. I could get these guys to work as a team, though, because VRRP is nearly identical. It operates the same in almost every way as HSRP. So this is nearly identical to HSRP. We could say that it's its cousin protocol, but it's vendor neutral. So we could run it between Cisco and HP or Cisco and Juniper or whatever vendors you have that support it. So to validate a configuration, you could use show standby, because all the commands that we use to configure it are standby commands. You'll have a group number, and this group number corresponds to your virtual MAC. See the virtual MAC 000, 0C, 07, AC, 01? It was this part that's based on the group ID. So I could just go to a public network, like the airport, and I could look at my gateway, and if I see 000, 0C, I go, hey, look, they're running HSRP version 1. And when I look right here, I can say their virtual router has a virtual router ID of 1. That's pretty cool, right? You could determine that just by looking at the MAC address of your gateway. And then you can hack things later. They've got ways to spoof HSRP messages, and you can become part of that group and do cool man in the middle attacks, which is half the exciting part about learning on how all this stuff ticks. Lots and lots of fun to be had with this. Not from a hacker perspective, just from, an understanding networks, and you could be a complete stranger in a network and kind of look at the MAC address of your gateway and get some good information about what's happening there. In HSRP, we have the concept of an active router and a standby router. The active router and standby router hear each other. They know about each other because the active router is sending hellos every 3 seconds to a multicast group. He's listening to those hellos every 3 seconds, and if you miss 3 hellos, we consider that a failure. VRRP is similar, except it sends hellos every second. So some people say that it's chattier, but it's faster to converge. If that bothered you, though, you could go into HSRP, and you could just change this timer to go faster or slower. Slower is going to result in less traffic, but also slower convergence. Most people prefer to things that fail over very rapidly. So the active router is responsible for responding to ARP requests. He goes, the virtual IP equals the virtual MAC. That's what he tells the world. It assumes active forwarding. In other words, he's doing all the routing for the network. He sends hello messages to let his partner know that he's there. And of course, he knows the virtual router. He knows the virtual router's IP because he's acting as a virtual router. Standby router is listening for those hello messages sent 3 seconds or 1 second by HSRP or VRP respectively. And then if he stops hearing them, he takes over the role of being active. So he takes over the virtual IP and takes over the virtual MAC and starts moving packets if we quit receiving hellos. So there we are. That is enough about HSRP for you guys to get the picture. If you understand this much, I would say VRP basically does everything the same up until this point. How are we doing so far? Thumbs up if you feel good about this. Thumbs down if it looks a little scary. Super easy. All right, is it going to freak anybody out if I said this could be a 3560 switch over here, and this could be a 3560 switch over here? Because many times the default gateway of your users is not actually a router. You've got an environment full of layer 3 switches, and then you have a router at your edge typically. So HSRP could run on routers, but it also runs on your switches. All right, so nothing scary yet. So my next question, how many of you, and myself included, we've got 12 people in class at the moment. Out of the 12 of us, how many of you have seen multiple broken Cisco routers? Like the Xbox One. I go, Mark, what's going on with your network? And you go, oh, another ring red of death on my Cisco router. I don't know where they build these things. Okay, Mark says never. Never's a pretty good answer. I've worked for co-location facilities that have got millions and millions and millions of dollars in hardware each year. I've worked for training companies that have got tons and tons of hardware. I have seen some broken hardware, but I haven't seen much of it. I've seen fans quit working. I've seen devices that got hit by lightning. It's not impossible for these things to die, but they typically don't die. Chris has had a really rough week. He's had two 3750s die on him, so he's not drinking my Kool-Aid right now. He's like, I don't know, man. I've had to replace 2 pieces of hardware. Now, the hardware itself is pretty reliable. That's all that I'm saying. If we have a network outage, it is typically not because the router died. When the users come to me and they go, Ryan, what happened? The network went down. I dropped my phone call. I go, oh, well, the router burnt out. That's not typically my answer. What's typically your answer if the internet access goes away? And you could all have different answers. I know what my answer is typically. Just wondering what yours is. Last time the internet dropped, what was the problem? Was it failed hardware? Okay, in Raymond's scenario, happened to be the connection to the ISP. Is that really weird, or is that anybody else? Because I'd say 99 times out of 100, if I've got issues, it's something to do with this last mile or some change with a peer or colo facility. It's almost never, and I'm saying almost for Chris because he's had some hardware issues this week, but it's almost never these guys. So why do we have these special protocols that cover our default gateways if the default gateway probably isn't going to break? Well, we made these protocols smarter. We gave them the ability to do interface tracking. So watch this. If my router is online, let's say that this is VLAN 127. If my router is alive and active on VLAN 127, the active router is continuing to send hellos, and the standby router thinks everything's completely fine. Now, there's a problem with this particular digital circuit. My FiOS circuit on router 1 has failed. What's going on with HSRP? He doesn't see any problems. He goes, hey, I'm still here. So as far as we're concerned, all the users are going to send their traffic to R1. And what happens? It's going to get dropped. Alternatively, it could go through R2 as kind of like a less efficient route. Depends on how your routing's set up. But ultimately, if router 1 doesn't have a connection to the internet, he's down. He's not doing us any good. And this is normally where most of my problems occur. And they should, right? This could be miles of fiber or miles of copper. There could be construction involved. There could be a fire. There could be a backhoe. Who knows? So if that router goes down for some reason, we want the other one to detect it. You guys with me? So here's what happens. Let's talk about the role of active and standby. Active and standby is something that's going to be determined through an election process. The device with the higher priority will win the election. By default, everyone has a priority of 100. So if R1 is the router that I want to make active, I can set his priority to 105. This guy has a default of 100, and with HSRP, a higher priority is better. So with the higher priority, R1 is the winner. He's going to be the active forwarder. Is everybody with me? So far, so good, right? Easy stuff. If we watch what happens next, we can turn on interface tracking that says, hey, router, great to see that you're up and running, but I want you to keep your eyes on this interface. If this interface ever goes down, I want you to subtract 10 from your priority. So he's going to decrement his priority. He's going to say, if that interface fails, my priority is now 95, which means this is better suited to be the lead. And he can take over. This requires a feature called preemption to be enabled. Preemption says, I'm going to go ahead and interrupt the leader because I have a higher priority number. Even though there's not a failure, I'm going to trigger a failover event. Everybody okay with that? So we can do interface tracking. If the interface drops for some reason, This is way outside the course of CCNA, but I bet some of you have this in your environment. There's something called IPSLA, that's service level agreement. You can basically do tests across the network out of this router. I can do a continuous ping, and I can keep my eyes on latency. And I can say if the latency is greater than 200 milliseconds, I want to decrement my priority, and I want the other router to take over. So you could do it based on traffic conditions. That's fancier, but it doesn't really change what's happening. We're just going to decrement the priority, drop our priority down, make sure the other device takes over with preemption being enabled, and traffic will go through the alternate device. So can HSRP do load balancing? And you're looking at the slide and you'd say, I would imagine yes, because the slide says this. I would say no. HSRP can do load sharing. And it's important that we understand what we're talking about early on, because we're selecting technologies based on their capability. What you do with this, and Mark's right, you can do this on a VLAN by VLAN basis. So I can say for VLAN 10, the gateway's here. For VLAN 20, the gateway's there. Well, that's load sharing. Load sharing is being accomplished by sending different traffic to different destinations. This is not load balancing. Load balancing is achieved with GLBP, where we've got multiple routers involved. Could be 2, could be more. And these routers are communicating. Let's say that this guy's the master. The other standby devices are telling him, hey, I've actually got 30% utilization. This guy says, I've got 27% utilization. He's got 36% utilization. And what happens is you've got one virtual IP, but you have many MAC addresses. Watch how crazy this is. Each participating router gets a different virtual MAC. And when a client, like client A, sends out an ARP request for .1, or whatever you set your gateway to, the master looks at the load and he says, you should go talk to R3. Now let's say R3's utilization comes up to 31%. A new host sends out an ARP request. You see where this is going? And the master is monitoring the utilization of the other devices. And he goes, oh, well, router B, the one in the middle there, is got the lowest load. So as far as you're concerned, .1 equals R2. So each of your clients is pointing to a different router, and this is all being managed dynamically through ARP. Should any of the routers fail, the other router will take over that MAC address. So this is, we kind of jumped from HSRP to GLBP, but this is load balancing. There's information being communicated about load. And then based on load and incoming connections, we're distributing them based on utilization. That's what true balancing is. What you see here with HSRP is load sharing. It's cool, we're using both of our routers. There's just not any intelligence involved in the path selection. So here's GLBP. This is what I was describing. It allows us to use all of our resources without the administrative burden of creating multiple groups. What you saw with HSRP, to get load sharing, I had to create different groups for different VLANs. Mark says, does that run on routers or switches? Both. A lot of times they're showing you pictures of routers, but most customer networks, I'm looking at these devices, and HSRP is going to be a layer 3 switch. GLBP could be a layer 3 switch. Just depends on what your environment is. I mean, right now, this is a poll for 12 of you. Everybody should participate. Is your gateway the router that's connected to the internet? For me, it is. There's 3 layer 3 switches I've got to cross before I get to my ASA. But my gateway is the device at the edge that connects me to the internet. In larger organizations, your gateway is typically a layer 3 switch. And you point to the switch, you have redundant switches. Should one switch go down, the other switch can handle it. Just depends on how big your environment is. GLBP provides a single virtual IP, but multiple virtual MAC addresses. That's what you saw before. It routes traffic to a single gateway, but that's distributed across multiple routers. In other words, everybody's gateway is .1. or whatever you choose to use. However, the MAC address, the .1 equals, is going to be questionable. Depends on who's got the lightest load when you ask. In the event of a failure, it automatically handles the rerouting by moving the virtual MAC to a new router and sending out a gratuitous ARP. In other words, a broadcast frame to tell the switches that that MAC is now located over here. Our GLBP output can be seen with the show GLBP. We can see what the virtual IP address is right here. You see that we've got a standby of 192.168.2.2. That's our neighbor who has a priority of 100. We've got 2.1 and 2.2. Doing a show GLBP, they say there's 2 forwarders. That's what we call the routers that are participating in our virtual router group. Each device is called a forwarder. So you can see their MAC address. You can see the MAC address that's actually handling this virtual MAC. And we can see that the state is active. All right. Not terribly scary, right? That was first hop redundancy protocols. Any questions before we wrap this up as a subject? We didn't actually see the commands to configure them, so let's see how bad it would be. We'll just jump over here and take a look at HSRP configuration. So configuring HSRP group for IP version 4. We go into global config, we go into our interface, we give it an IP address and subnet mask. Everybody knows how to do that. Then we can say HSRP group number and then give it a group number. HSRP group number. That's it. Looking at, let's take a look. This might be for version 2. I was expecting to see standby commands. You know why? Because this is on a Nexus 7000. That would be the problem. So let's do HSRP configuration on iOS. I was like, those aren't the commands. We need to see show standby. So configuring, let's see. And you know what? We could be more specific. Let's look for a particular switch. Let's just do this from the top. Instead of using Google, you can't just always Google for a configuration because the configuration will vary based on the version of code and the type of switch. So I'm going to go to the support page and then go to switches. And then here's all the different switches. What we do is we log into our switch and just issue a show version. And I can see here I've got, let's see, 12.2 code, 12.255 on my 3750. And I can tell it's a 3750. Right here, where it shows me the actual model number, 3750X, 24 ports. So coming back to Cisco's site, I say I've got a 3750X. Next thing, we go how many? We've got 24 ports. And then there's going to be documentation that we can now find. And we've got our configuration guides here. So 3750, 3750X configuration guide for 12255 SE. That's what I'm running. This is the doc that I want. Now on the left-hand side, we've got all the categories. And the first time I came in here to configure something, I was like, you gotta be kidding me. It's not the easiest thing to navigate, but navigating Cisco documentation is a skill, just like subnetting or anything else. We could try to search the document and try to find HSRP, but we could also go through and we could take a look at the different categories. So here we've got a title right here, configuring HSRP. Sometimes you'll see a title that says configuring first hop redundancy protocols. So they all start off with understanding it, so talking about how it works, And if you're unclear of exactly what you're going to do, I always say there's no time like the present. Take 5 minutes to read this over, make sure it's got the right solution. Next, they show you a typical diagram. And what are they using here? Are those icons for switches or routers, guys? I know it says virtual router, but that's an icon for a switch, right? Your routers are round with arrows. Your switches are square with these other arrows. So these are switches, and they're going to set them up within an HSRP group. If you look at the configuration for it, scroll down here, we use standby command for everything. So config T, and I say standby, and I give it a group, like 1. And then I can give it an IP address. So standby 1 IP address, and I give it the virtual IP. So let's see if we got some configuration examples. Here. So what this router's doing is he's working with 2 different groups. He's going to use the virtual router 10.0.0.3, and that's part of the 10.0.0.1 subnet. So maybe he's .1, maybe the other router's .2, and the virtual router's .3. He set his priority to 110 to make sure that this device is the virtual router. You with me? And then on the other device that's your partner, you make him a priority of 110 for standby group 2. If you don't specify priority, you've got the default of 100. And here we're making sure that preemption is enabled. And that says if you have a higher priority than the other guy, you should take over. That's all it takes to configure this. They don't show it within our slides. And I also said the timers are set to 3 seconds. You could drop that with the standby specify the group number in timers command. So we could drop that down. How are we feeling so far? So far, so good? If it were me, I would say it looks really easy, but I need to test it myself. Well, here's an example of what's going on. This is perfect. We've got router A compared to router B. And like I said, router B's got a priority of 110 for standby group 2. Over here, we didn't set one. These guys are backing each other up. The part with decrementing from your priority is if you do interface tracking. So let's see if there's any lines in here about tracking an interface. Now, enhanced object tracking is a little fancier. Standby track interface configuration ties the router hot standby priority to the availability of its interfaces. This is what we're talking about here. There's a standby track command. And then what happens is if that interface goes down, priority decreases by 10. And they use it in their example here, that you can configure interface tracking. You can set how much it drops by, but the default value is by 10. Cool. So this is something that it's easy to understand, but it's important, right? If the gateway, if you set this up and it doesn't work the way that it's supposed to, it's a big deal. Everybody's offline. So you saw it here and you go, okay, it's really easy. Just use the standby command, use a pair of routers or layer 3 switches, and I should be good to go. Sure, but then test it and make sure that it works the way that it should. Unplug one of those routers, make sure the other one takes over, and do a continuous ping. See how long until you can get back out again. You can configure this in the Boson NetSim. So if you don't have NetSim downloaded already, you should get it. Download it and just set it up within the lab, see how it works. That's the point for me that I'm like, wow, this is as easy as I thought it was. Or maybe there's more questions that I have. In either capacity, you don't really know what you know or don't know until you try it in hardware. So, and I say that loosely, a simulator, same thing. So whether you're using NetSim or GNS3 or you've got some live hardware available, the commands are going to be the same. Give it a whirl, let me know what you think. All right, so looking at where we're at for time, doing pretty good. This was our main topic for the first part of the class. Let's go ahead and jump into our break, and when we return, we'll get into network troubleshooting, because that's what's going to pay the bills, right? I'll see you guys after the break. And as always, if you've got any questions, just put them in room chat and I'll address them as soon as the break's over.